Hello everyone. Let's start. Today we have Ravi. He'll be talking about provably tuning the elastic net across instances.
Thanks, Tim. Hi, I'm Dravi, and this is joint work with my advisor Nina Balkan, as well as Misha and Amit. And this work appears in Europe's in the coming conference. So this is something you've probably seen in your ML or Stats 101 course. We are given some data set X, Y, and we want to fit some this least squared regression where we want to fit beta, which basically allows us to find the closest approximation of Y using the features X. So in some sense, we're trying to fit a hyperplane. We have M examples. Each example consists of a feature vector, a p-dimensional feature vector X, Xi, and also a dependent variable Yi, which is what we're trying to predict. And our goal is essentially to fit that hyperplane so that we minimize this loss, which is the squared loss of the distance between our hyperplane and the value Y, which is the true value for that variable, for that example. So one issue is if we try to do this using this OLS or ordinary least squares, you would end up, and suppose you have too many features, you would end up overfitting your training data set, and you can essentially minimize this loss by appropriately selecting beta. In fact, you have a closed form for beta, but it may not turn out well in practice. For example, if you get a new example from the same distribution or same problem family, you might not get a good value just because you're overfit on your training set. So the common solutions, again, these are something that are taught in introductory courses in stats and ML, are using regularization. So the regularized linear regression looks like this. You add a term lambda times the L1 norm or squared L2 norm. These are well known for a long time, and the intuition is these somehow allow us to learn a better value of beta than the overfit value, and the intuition is captured in these pictures. So you have these squared loss contours. So your the center points of those ellipses are essentially just the beta hat from OLS, and instead you want to select these beta stars, which are which somehow also have a low value of these additional regularization terms, right? And there are nice properties for L1 and L2. L1 gives you sparse features because, for example, in this picture, it's setting beta 1 to 0. It's selecting beta 2 as the feature. L2 has also some nice properties. It in this picture seems to uniformly sort of shrink all the features. But it works. It also is L2 is something that can work even when you're in the over-parameterized regime, which is basically when the number of features is more than the number of examples. Right. On the other hand, we have limitations of these individual methods. So the advantages of one turn out to be limitations of the other. So L1 doesn't work well if your number of examples is less than the number of features. In this case, the L1 solution will always select at most M features. It cannot possibly select more than M features. And also L2 in general has issues like it's not sparse. If, for example, we want to identify which variables are more important than the others, then we want to prefer L1. So a workaround, which is almost 2 decades old, is the elastic net. Here you have a linear combination of your L1 and L2 regularization. Yeah, so it turns out this solves the individual limitations of both these methods, right? By appropriately choosing your lambda 1 and lambda 2. So that's the main question of this talk. How do we set lambda 1 and lambda 2 for a given data set or a given problem space you're in, right? So typically what people do in practice, you use a holdout data set. So you would split your training set XY into X1, Y1, X2, Y2. For X1, Y1, you would find, you would solve this minimization problem. You find for each value of lambda 1, lambda 2 on a grid. So you would take a grid of solutions. So essentially, you consider finite number of combinations of parameters. There's some inefficiency there, but also at the same time, you're not really considering the entire domain. You're considering only a finite number of parameter values. And for those parameter values, you find the beta elastic net, which is essentially this minimization. And on the validation set, you see how well that generalizes to the remaining examples. You don't always just do a single split. Typically, to make it more robust, you would do like several splits. You would maybe take the several random splits of the data set, or there's also this leave one out cross validation where you would just leave one example out and compute the holdout loss on that example and do that over all examples essentially. So there are several ways to do it, but that's the high level idea of how people try to set these lambda and lambda 2 in practice. So, but the problem with that is we don't have nice guarantees how well do they perform on this on an unseen example. So we want to essentially give some kind of guarantees on how well your choice of lambda and lambda 2 performs on unseen examples. So we'll be considering this, formally we'll consider this multiple instance setting. So you have n instances of the regression problem. So you're potentially learning from several data sets or several examples. Maybe you're getting new data sets every day, and each data set is of the same form. You have xi, yi, which is what you will be training on. There is a split of xvel, yvel, which can potentially overlap. So we don't make any assumptions on whether or not there is an intersection between the validation and training set. And so the idea here is we can also change the number of examples and features in each data set. There's no requirement on having the exact same number of features or examples in each data set. We just assume there is an upper bound on the number of examples and number of features. So we denote this problem space by pi and p. Okay, and as we talked before, we want a validation loss on some. So on any data set x prime y prime, we define validation loss of regression fit beta as this average squared loss over that data set. So for the elastic net on ith problem instance, our loss function essentially is just for problem pi, we will train our elastic net using the left side xi yi, and we'll test it, or we'll compute the loss on using the validation part. So that captures several settings of interest. For example, cross validation, which is the most common thing. There's also several multitask formulations where each problem instance comes from related tasks, which is also captured by our setting. We want to identify values of lambda and lambda 2 which work well for several different but related tasks. Right. So with this formulation, we consider two distinct settings. So one is the so-called distributional setting or statistical learning setting, where problem instances are coming from some problem distribution D, right? So each PI is sampled from some distribution, and we want to minimize the loss on some random problem instance coming from D. So that's a standard learning setting. And we'll also consider an online setting. So you will have T problems appearing online, the ith problem PI. So each time you see the training part of the training set of the problem PI, and the learner would predict some values of the parameters, the regularization parameters. After you make the prediction, the validation set is revealed, and you would suffer some loss on that validation set. And the goal is to minimize the relative regret to the best possible choice for that sequence. So this concludes the setup part of the talk. So we have introduced all the definitions and formulations. The rest of the talk will be a set of results that we have for the setting or settings that we discussed. Right. We'll start with the general structural result for the elastic net, which applies to the loss function of the elastic net. Okay. So so we need a definition of the so-called piecewise structured functions, which just maybe we'll use a simple running example. Suppose you have this piecewise constant function where in two parameters, and the pieces are separated by hyperplanes, and the pieces themselves are constant in each region. So when we consider a strong generalization of this, so real valued function class is f, g, k piecewise decomposable. F is a set of real valued functions, which we call the piece functions. So here they are constants. We could be they could take any arbitrary form. So we would want to characterize our loss function in terms of some piece functions as well as some boundary functions. So these are the boundaries in the picture. They're hyperplanes or lines in 2D, but yeah, in general, there could be any functions. For example, we'll see algebraic boundary functions in this talk. And yeah, k is a positive integer, which denotes the number of boundaries that we have in the function. So for each function h in this class, you can take k boundary functions from the function class, boundary function class set, and for across those boundaries, each piece must have function of the from the f function class. So that's essentially what piecewise decomposable or piecewise structured function is. We also need this notion of dual function class for a loss function. So remember, our loss function of the elastic net depends on both the parameters, as we defined, it depends on both the regularization parameters, which are used to train your beta on the training set, as well as the problem instance itself. The problem instance is used both in the training phase as well as in the validation to define the loss. Right. So we can define a primal function class if we fix lambda and lambda2 and we vary the problem. So that's typically the function that people have studied before, and it's a hard function to study. But in this talk, we'll look more at the dual class. So we'll fix a problem instance, and we'll see what the complexity of the loss function can be as we vary the parameters, lambda and lambda2. So this brings us to the main result. We essentially show that the class of loss functions for the elastic net, particularly the dual class, is piecewise decomposable, where our piece functions are rational functions with bounded degrees, and our boundaries are polynomial threshold functions, again with bounded degrees. Right. So in the picture, again, this doesn't capture the exact nature of polynomials, but just to depict the things we have. So we have these two parameters, lambda and lambda2, and we can divide the space of parameters by these polynomial boundary functions. So there are these two R1 and R2 polynomial functions, and for each partition of the space by these polynomial boundaries, you would have a fixed value of the piece function. And the piece functions are rational functions. Note that the piece function, in this definition, we require the piece functions to be the same for a given sign pattern for the boundary functions. So, for example, that doesn't have to be a contiguous piece, but as long as it's on the same side, so it doesn't need to be contiguous for at least for algebraic boundaries. They can be for the same sign pattern. They can be two disjoint pieces. So this is our kind of crucial lemma. So yeah, under standard sort of assumptions, we consider positive values of the parameters, and so what this lemma is stating is that suppose we fix a subset of the parameters of your feature space. So E, which we call the equicorrelation set or the active set, is basically the set of parameters which are going to be non-zero in your solution, beta hat. So the solution beta hat will have some non-zero values, and those will exactly correspond to this set E. And S is a binary vector, again, the same dimension as the number of features. So we can give the exact closed form provided we know this this set of the subset of features which are non-zero in our solution. And the proof of this uses a reduction of the elastic net to lasso, which was the L1 regularization problem on a transform data set. And it also uses characterization of the lasso solutions and some simple algebra. So one thing to note here is that each, this matrix gives us some indication of why we get those rational polynomial piece functions. So again, elementary algebra, you can linear algebra, you can show that these inverse matrices would have each entry of these inverse matrices would be a rational polynomial in the lambda parameter. Yeah, and combining that, we get the full result. So in a few high-level steps, we apply the lemma A, which implies that the regression fit and also the loss function is a rational polynomial function, but for fixed subset of parameters which are non-zero. And we then use KKT conditions to show that any connected region with fixed value of E and S is bounded by algebraic curves, which are those polynomial thresholds which we talk about, and there are at most p times 3 to the p such curves. So for any fixed sign pattern of these curves, we show that the set set E and S is fixed. E is the set of again the positive non-zero values in the solution, and therefore these piece functions are rational polynomial functions.
So if each intuitively we're saying each piece is defined by the set that is non-zero,
yeah.
Wouldn't we expect there to be 2 to the p curves if there's a binary choice for 0 and
there's also, yeah, so there's this sign vector. The 3 to the p comes from there. You also vary the sign. It's a sign set. It's not an unsigned set. Yeah, we also, it depends also on the sign of the essentially the sign S captures this sign of the correlation of the variable, which is correlation of beta with the data set. And yeah, so essentially that 3 to the p such curves, and there's an additional factor of p, which is again, it's a loose upper bound. It's not necessarily tight, but the p factor intuitively comes from we consider the conditions at which any variable can enter or leave that that active set. And those are exactly the KKT conditions. Okay. So yeah, so that's the main structure, and essentially what we've done here is that we've shown that the loss function has some kind of polynomially, roughly speaking, bounded complexity for both these boundary functions as well as its behavior inside within each boundary is also polynomial bounded, or this rational function. So this was the main characterization of this loss function, which we prove, and then we use this structure on the loss function to prove learnability results on the which we call the distributional setting or the generalization setting. Okay, so for this, we'll need one more definition. This is a standard definition from learning theory, but it also, if you've seen VC dimensions, which is taught in most ML courses, this is generalization of VC dimension to real dimensional functions. So VC dimension is for binary valued functions, it's for real valued functions. And essentially, yeah, it generalizes this notion of shattering a set of endpoints. So you're given endpoints from your input space, and you essentially want to say that your function class is strong enough to label these endpoints in all possible 2 to the n combinations. Right. So yeah, so that's intuitively speaking what this definition is doing. And yeah, so pseudo dimension is essentially the largest possible set that can be shattered or labeled in all possible ways by your function class. And the classic learning theory result gives a generalization guarantee in terms of the pseudo dimension. So suppose you have bounded real valued functions, and you have a bound on the pseudo dimension, then for any error target epsilon and confidence value delta with the with probability at least 1 minus delta with high probability, you can show that the sample complexity of epsilon delta learning the class H is at most this. So epsilon delta is just uniformly learning is just saying that with probability delta, you would be with at least 1 minus delta, you would be within epsilon of the best possible loss in that. Yeah.
I have like a couple
Yeah.
questions about this slide, which may be unrelated, so feel free to read them.
Sure.
First, is this second result reversible? Like, if you are learnable by some algorithm with some sample complexity, does it mean that the pseudo dimension is upper bound?
That's a very good question. So we have, I know, like lower bounds, like in terms of for the VC dimension case, there are known lower bounds. But for pseudo dimension, I am not sure if there are known lower bounds in terms of the sample complexity. Given, yeah, if you bound these lower bound these pseudo dimension, can you also lower bound the sample complexity? For the analogous notion for two binary classes, we know that it can be lower bounded.
And the second question also related to this real value version.
Yeah.
So I know the result from this dimension. Just want to find out like what's going about this real value version. So there's also the notion of Rademacher complexity,
yeah,
which also governs generalization for real functions. So you know what the relationship, if any, is pseudo dimension and Rademacher complexity?
Yeah. You can bound the Rademacher complexity using the pseudo dimension as well. So pseudo dimension gives a way to bound the Rademacher.
And is the reverse relationship, like, are they equivalent or?
They are not equivalent. Again, it goes only in one direction as far as I know. Yeah, so I think these can give you a nice upper bounds. The kind of lower bounds we've been able to show are like lower bounding the pseudo dimension, but it's not clear if it gives a lower bound on the sample complexities. So just to clarify this uniform learning bit a little bit more. So for any distribution D, any accuracy parameter epsilon given sample S of size of the above size, we have with probability 1 minus delta that this big O size with probability 1 minus delta the function with the smallest average error over S. So that's just something you can compute by iterating over your function class. You can find the empirical error minimizer. So if you minimize the error on the sample, that should give you guarantee you to be within epsilon to the optimal choice of the function over the distribution D. So that's what we mean by generalization. So for any example that you any problem example that you draw from the distribution D, your the H that you will learn will also have error at most epsilon.
So the function, so the minimum that you're taking here is over the whole class C, or like some cover of C? Sorry, what did you call H? Sorry.
H, yeah.
So when you say the minimum here, is it like the minimum over all possible infinitely many functions in H, or like some finite cover?
It's overall in H. So yeah, if it's a finite class, it would be easier to compute the minimizer. Even for some infinite class, you can compute the minimizers, but again, it's not clear when can you give efficient algorithms.
No, but like for the definition of uniform learning, like two notions probably make a difference.
Yeah. So we consider over the entire set H. Okay. So yes, these are central learning theory definitions, and our results would be in terms of bounding the. So yeah, just to give a preview, we'll try to bound the pseudo dimension for the class of loss functions for elastic net. So essentially, we define this HEN, which is essentially just all the loss functions for the elastic net as you vary your parameter lambda and lambda2, and we show that the pseudo dimension of this is upper bounded by p squared, where p is the number of features. Okay, so here's again the proof sketch. So we have we give this. This was a motivation for why we did this piecewise decomposable thing. So essentially, those sign patterns in the piecewise decomposable definition are related to the sign patterns in the pseudo dimension definition, and what we do need to do it in addition to that previous structure is that we also bound the complexity of F and G. So it's in particular we bound the pseudo dimension of the dual F, which so remember F was these rational functions, we show that we use a simple lemma which says that if you have any k algebraic curves with degree at most p, we can bound the number of pieces they induce in a 2D plane by a polynomial in p. And for pseudo dimension, you want to be able to generate all 2 to the p sign patterns, which means the pseudo dimension or the number of maximum number of curves you can have is at most log p. We also bound the VC dimension for G star by OP. Again, this is relatively straightforward. It follows from standard arguments for you can give these arguments for you must have seen these for linear threshold functions. We extend them to polynomial threshold functions. It's not too hard. And finally, we combine these results using a powerful result which gives the complexity of the piecewise complexity of bound on the pseudo dimension of the piecewise structured function class using the corresponding by using the complexity of these piece functions and the boundary functions. Combining all these three results gives us essentially, roughly speaking, we get a p term corresponding to this complexity of g and these boundary functions, and we get a p term corresponding to a logarithm of the number of these boundary functions, which was, remember, 3 to the p. Right. So so this implies using that learning theory result that we have the sample complexity of tuning the elastic net. If we see enough problem instances from coming from the distribution D, then the parameter, the regularization parameter that we will output for the elastic net using just the ERM over the sample minimizer would with probability at least 1 minus delta give this guarantee that your value of the learned parameter over the distribution over the best possible parameter differs at most by epsilon. A simple corollary of this is for many popular cross-validation techniques like leave one out cross-validation, or there is also this Monte Carlo cross-validation where you do a random split in a fixed proportion and you do it several times. So we show that these many iterations of cross-validations are enough to guarantee epsilon approximation for the loss for the generalization. We also show that our results not just hold for the squared loss. You can essentially give the same guarantees even for more challenging loss functions, which are also used much more frequently in practice. This information theoretic. So these are essentially, you added some additional terms to your loss function, which depend on essentially the L0 norm of your beta that you've learned. Essentially, just modify the. They also capture the model complexity just in terms of number of non-zero terms in beta. And our results, it's easy to show that our results also hold for these other loss functions that people commonly use when they're doing this holdout validation.
Question on the corollary about cross-validation. Maybe I'm not understanding something. It seems like this is saying that your regularization parameter would do well on the task of the cross-validation task, but not on the main task you actually care about of performing well on the big data set.
Right.
So that's like an extra assumption in the cross-validation.
Right. So this so this is a guarantee that how many iterations of cross-validation are enough to, when you should stop cross-validation, it would stop improving after this point. It would not give anything additional.
Okay, there's no reason to do any more cross-validation.
Yeah, that's what this corollary gives, because typically when leave one out, you would do order M, which can be much larger than this. Okay. That's a very good question actually. So in general, our results apply to a much more general thing where you potentially have related tasks. Not even, so this cross-validation is a very, very special setting where you are just splitting the same training set several times. So those were our distributional results. We also have some online learning results, essentially the setting where you have, remember you had these T rounds, and in each round you're trying to, you see a new data set and you're trying to predict what value of the regularization coefficients to use. So for the online learning results, we'll need a couple of simple assumptions. First assumption is the boundedness on all the variable and on the y and x values, all the feature values and y values are bounded by some large constant. And we also want a smoothness assumption. So the predicted variable y are drawn from, so this is an interesting assumption. So we want that the values of y, if you change them by just a little bit, it doesn't make much difference. So essentially what this says is the probability there's this probability density function for joint distribution of these yi variables, and we assume there is an upper bound on the probability density. This is justified by what people actually do in practice. So in this popular Python library, scikit-learn, which implements these elastic nets, there is this jitter parameter which adds uniform noise. And the motivation is that this helps generate more stable models. For example, if you're trying to do feature selection, if it depended very strictly on the values of y, you might get like different features are important. If you just keep a fixed value of y, but by adding this jitter, you can get more stable outputs in terms of what features are important, for example. So people, generally add this jitter, and this corresponds to, this sort of motivates our assumption that we want to allow yi to be coming from some smooth distribution. So under these two assumptions, we show that there is an online algorithm which has expected regret bounded by square root of t. I have suppressed terms which are logarithmic in t, and other parameters which are polynomial and other parameters, but I've suppressed the dependence there. So the main idea here is that as t increases, the expected regret only increases sublinearly, which means we converge to the optimal, to the performance of the optimal parameters at rate 1 over square root t. And again, as before, the results also hold for losses adjusted by popular information criteria. Again, I'll go over a very high level idea of the proof for this. So previously we proved that the loss function has a certain structure. We sort of extend that argument further. What we need for this, in addition to that structure, is that not only do the functions take a certain form, which was enough to give the generalization guarantees, we also show that the functions do not concentrate in any region of the parameter space. For this, we crucially need our smoothness assumptions and the boundaries assumptions. Right. So essentially, what we want to show that if you consider the several problem instances, you had to remember those piecewise, the boundaries of these piece functions, and we essentially show that over several instances, if your yi's are smooth, the boundaries do not concentrate too strongly in any wall of the parameter space. And to do this, we use several prior results. In fact, the algorithm is also a prior known algorithm. We just prove that the conditions, the assumptions needed for that algorithm to work are satisfied by this, in this case as well, under the assumptions. So finally, we come to this, we extend our regression results to another interesting setting, which is classification using elastic net or regularized loss functions. So the setting here is, suppose you're now, instead of regressing, you have your yi's are restricted to binary labels, 0, 1 labels. And to classify, so remember, you can think of your the beta that you select and multiplying it with x, kind of projecting your featured data set into a 1D space. So now the natural thing to do is to apply some kind of threshold and use that for classification. So we have this additional tau here, which in our problem, we even treat this as a hyperparameter. So you can even learn a good value of tau across different instances. Right. And the loss function now is a 0-1 loss on the validation set. So yeah, so 0-1 loss is just whether your labels, you suffer a loss if your labels match the, do not match the true label, for that example. So for this setting, we study Ridge, which was L2 regularization, lasso, as well as elastic net. And we give bounds on the, again on the pseudo dimension, which imply generalization guarantees for these settings. Right. So a few comments here. So we have yeah. So we have at most m examples in each of our problem instance, and each at most p features. So we show that for L2 regression, there is this nice logarithmic bound on the sample, which implies a logarithmic bound in sample complexity, pseudo dimension. As well, for lasso, we also study this over-parameterized regime, which we were not able to study for the regression problems. It's, I guess, interesting open question how to study the over-parameterized regime for regression. But at least for this classification problem, we are able to give a bound on the pseudo dimension for just L1 regularization, not the elastic net, which is linear in M. So that's an interesting question. Where P is much larger than M, can you give better bounds? Which for those settings, our bounds are probably loose for the regression setting. And finally, yeah, for elastic net, we give a bound, which again, it essentially extends the piecewise structure and the argument, which we've already seen. The nice thing about the Ridge pseudo dimension is we can give a proof from first principles. So I'll go over a quick proof sketch. It's not too hard to prove. Right. So for L2 or Ridge regression, you have an exact form for what your beta hat is going to be given your problem instance xi, yi. Right. And as we saw in the previous proof as well, and there's this inverse there for which each entry is a rational polynomial, in this case just lambda, and the degree of this polynomial is at most pi. Both the numerator is at most pi minus 1, the denominator is at most pi. Right. So with this structure, we do a prediction on well, yeah. So we show that the prediction on it follows from this that the prediction on any validation example. So basically, we have a bound on how fast each coordinate of beta hat can vary with lambda, which means the y hat that we predict on any validation example changes at most p times as lambda varies. And we have at most m examples in our validation set. So this implies at most n times m times p different possible values of the loss function for n problem instances. But in the definition of pseudo dimension, we need at least 2 to the n different loss function values to be able to generate all the sign patterns. So just say, yeah, just combining those two observations, we get that the largest problem set that can be shattered is of size log n. Yeah, to summarize, we have we show that we can learn elastic net across instances with polynomial sample complexity. So that's, I guess, the key takeaway or the main result that we have. But I think we also have several interesting open questions. We do not know at this point what are good lower bounds for either the structure or all the sample complexity. For some other problems we've shown, we've been able to give lower bounds at least from the structural complexity, which means like you can show that the pseudo dimension at least is lower bounded by, or we can give even tight asymptotic bounds of the pseudo dimension. But here it's not even clear whether our bounds are tight. We do have upper bounds which seem useful. The other very interesting question is to make these things, in order to make these things practical, you need or implementable, you would want polynomial time algorithms, right? So and the empirical risk minimization for elastic net over n problems is not it's not clear how to do it in polynomial time. And simpler question might be even to do it in output polynomial time. So suppose you have those algebraic boundary, the pieces of the with those algebraic boundaries. Can you compute those pieces in output polynomial time? So if your problem is nice enough, at least you can potentially solve it fast. So those are several interesting questions which are potentially can lead to interesting future work. Yeah, we also considered this more challenging online setting where we don't see the entire data right off. And we see each problem is revealed one at a time, and then we get this 1 over square root t kind of convergence to the best possible choice of parameter in hindsight. Yeah, this needed more assumptions on the problems though. We also solved the classification settings. Again, there we have upper bounds. So again, yeah, and getting lower bounds as well as efficient algorithms are interesting questions of future. I think that's pretty much all I have. More questions?
So you focused on maybe 3 regularization choices, right? So L2, L1, and like some L0 related things. What are the sort of special properties of those specific regularizations that makes this approach work where like some more fancy regularization function doesn't work?
That's again, that's a nice question. So yeah, I think the properties that we do end up using are so for L1 again. So one thing is these are like nice convex optimization problems, and in fact there are like efficient algorithms known for solving. So for just the L1 problem, there are efficient algorithms. What you can do is essentially compute a piecewise linear solution. So your beta parameter, the optimal beta parameter, is a piecewise linear function of lambda. Yeah, so you can essentially solve it for all lambda simultaneously efficiently. And for lambda 2, there is an exact closed form solution. Yeah. So yeah, for L2 there's a closed form solution. They are like some of the easiest for an arbitrary value of the norm. I think we don't know of nice forms for the solutions essentially.
If there's no other question, then